So, today, we're going to dive deep into the hidden language that powers, well, pretty much our entire digital world. It's this language of pure logic. And to really get a feel for it, we're going to kick things off with a fun little puzzle.
Okay, check this out. This is a scenario straight from an MIT warm-up quiz. Imagine you're a Pokemon master, and you've got one simple personal rule. You never go outside without a Pokeball. Now, based only on that rule, which of the statements we're about to see is absolutely, positively, 100% guaranteed to be true? No exceptions. Just think on that for a second.
Now, this isn't just some quirky brain teaser. The answer here actually unlocks a really fundamental concept in computer science. It's this idea of logical implication, which is, and I'm not exaggerating, the absolute bedrock of how computers make decisions.
All right, let's break this down into logic speak. Let's say you're outside is statement A, and you have a Pokeball is statement B. Our rule is super simple. If A is true, then B has to be true too. So looking at these options, which one perfectly captures that rule? Does it mean you're always outside with a Pokeball? Or does having a ball automatically mean you're outside? You got to think carefully about what the rule actually promises and what it doesn't.
Okay, so the big winner here is A implies B. It just perfectly captures the rule, if you're outside, then you have a Pokeball. The other options don't work because the rule says absolutely nothing about what happens when you're inside, right? You could be on your couch with a dozen Pokeballs or with none at all, and you haven't broken the rule. And that other one, not A and not B, that's really just a fancy double negative way of saying the exact same thing. It makes it logically impossible for you to be outside and not have a ball. So that if-then logic, it seems pretty straightforward, right? But what happens when rules aren't written in that nice, clean, precise logic, but in plain old everyday English? Well, as we're about to see, that's when things can get really ambiguous and even a little dangerous.
And this is a real-world example from an MIT computer science problem set. Students are literally asked to analyze their own class collaboration policy. And here, misunderstanding the rules doesn't just mean you get a puzzle wrong, it could actually mean you fail the course. The stakes are way, way higher.
So just look at these scenarios. Some of them are total no-brainers. Copying your old solution? Yeah, that's a clear violation. Using what you learned from a book? Totally fine. That's allowed. But what about a pop set party or photographing joint notes? The policy says to separate and write up your own solutions, but what does separate really mean? See? This is where language starts to fail us.
Let's just take that one scenario of photographing the notes. You could totally make a case for it being allowed. You could say, hey, we just got ideas together, but the final write-up was all me, so I followed the spirit of the rule. But then you could flip it around and argue that working from the exact same photo means your work isn't truly independent. Both arguments sound pretty reasonable, right? And that right there is the danger of ambiguity.
So how in the world does computer science solve this problem? How do you build systems that rely on billions of rules without them just collapsing under the weight of all this ambiguity? Well, you don't fix the language, you invent a whole new one. A language designed from the ground up to be perfectly mathematically precise.
And that language is called predicate logic. Its entire purpose, its whole reason for existing, is to translate our messy, fuzzy human ideas into crisp, clean symbols that have one and only one meaning. When you're writing code, you aren't having a nice little chat. You're giving extremely precise instructions in a language that is literally impossible to misinterpret.
Okay, here's a really famous idea from mathematics, Goldbach's conjecture. Now, in English, it's pretty straightforward. You and I can read that and understand what it's saying. But to a computer, words like even, greater than, or prime are just gibberish. They're meaningless text until they are defined with perfect precision.
Now look at that same idea written in predicate logic. Whoa, okay, I know it looks like a bunch of alien symbols, right? But it says the exact same thing, just with zero wiggle room. Let's walk through it. It says, for any number n, if n is greater than 2 and n is even, then there must exist numbers p and q, where p is prime and q is prime, and n equals p plus q. See? Every single symbol has one single undeniable meaning. And this is the crucial point. Once you have a language that's perfectly precise, you can start to build arguments, what we call proofs, that are completely logically airtight. You can demonstrate that a statement isn't just probably true, but that it is absolutely, universally, undeniably true.
So let's try a simple one from that same MIT problem set.
We're going to prove that for any group of things, we'll call that set A, it's always equal to the part of A that's not in set B combined with the part of A that is in set B. I know, it sounds kind of obvious, but in logic, you can't just say it's obvious. You have to prove it.
Okay, so here's how we build this totally unbreakable proof, step by step. First, just pick any random item, let's call it x, from inside set A. Now, this little x has only two possibilities in the universe. It's either inside set B or it's not, right? There's no third option. So if x is in set B, then by definition, it has to be in the part where A and B overlap. And if x is not in set B, then it must be in the part of A that's outside of B. Since those are literally the only two places it can be, we've just proven that any x in A has to be in one of those two combined sections. QED. The logic is unbreakable.
Now, I know this might seem like some really abstract mental gymnastics, but this whole process, building these unbreakable logical arguments, it is everything. It's the core skill that separates people who just use computers from the people who actually build our digital world. Every single app on your phone, every banking transaction you make, every little piece of your social media feed, it is all built on this exact foundation. That simple proof about sets we just walked through, it uses the exact same fundamental reasoning you need to build a complex sorting algorithm or a secure login system. It's all about breaking a massive goal down into tiny, verifiable, logical steps that when you chain them all together, create a massive system that works flawlessly, millions of times a second.
So I want to leave you with this final thought to take with you. This incredibly powerful tool isn't just for computers. Think about a rule at your job, or a policy in a club you're in, or even just an agreement you have with a friend. What's one ambiguous rule in your life that always causes confusion? And how could you rewrite it with the kind of precision we've been talking about today? Thanks for joining this explainer.